Welcome back to a new video. So what we're going to do is we're going to just do homework 1. There is a link in the description below, and that's where you can go see the questions. I do highly recommend to go look at the questions and try them out to make sure that you know how to do these questions, because they are very important, especially in the future. And pretty much this homework 1 is about all the videos that we did already, that we've done in the past. So it's very important for you guys to have done everything before. So let's get started on our first homework 1 video. This is all about chapter 1, and I hope you guys don't find it too difficult. So what are the essential building blocks for a computer? There's three different things. There's a processor. This processor, the CPU, it interprets instructions and execute programs. It uses the ALU and the control signals to use and implement the fetch, decode, and execute cycle. Then we have memory. We have to use some sort of memory. And when we say memory, we're really more talking about RAM, ROM, not necessarily ROM. Let's just call that main memory. RAM and ROM are main memory. Let's just call it either primary memory or main memory. And then we also have our registers, which is really high on the hierarchy of memory. It's the first. And then we have cache, but cache and RAM, main memory, are a little bit more um, non-essential to the the original proposed and basic structure of a computer. Usually cache and RAM were developed over time to implement in our computers. And then for last, we need an input or output mechanism. We need to allow the computer to receive data and send data in some sort of way. Without an input and output mechanism, you're just really just having just a machine that does its own self without asking anything from the user or even just from the computer. So, this is when we move into the portion of conversions. So, for the first few questions, what we're going to be focusing on is just the power of tens. So, it's asking how many milliseconds are in 3 seconds. If you guys remember that I usually use a kind of like stoichiometry type of conversion. So 3 seconds, 1 second, because I want to cancel out these, right? And how many milliseconds are in 1 second? It's 10 to the 3. So what we're looking at is 10 times 10 to the 3. And this leaves us with milliseconds. So it's going to be 3,000. Oh, let's try it one more time. It's going to be 3,000 milliseconds. Alright, moving on. So how many microseconds are in 6 seconds? It's going to be the same exact thing, except we are changing the conversion factor for microseconds, which is 10 to the 6. 10 to the 6 microseconds. So what's going to happen is seconds cancel out, and we're left with microseconds, and then we have 6 times 10 to the 6, which is going to be 6 million microseconds. And that's a second conversion. So how many nanoseconds are in 5 milliseconds? So 5 milliseconds. We want to convert this back to seconds. If you can just go straight from milliseconds to nanoseconds, it's fairly easy for sure. But sometimes it can get a little messy. So this is why I show it this way. It allows an easier conversion factor. So we want to convert back into seconds. So what factor of milliseconds goes into 1 second? Just like we did over here, it's 10 to the third. But we want to cancel out the units. So I'm going to have milliseconds on the bottom and I'm going to have seconds on the top. So you see right here, milliseconds cancel, we're left with seconds, and how we want to convert into nanoseconds. So we're going to do the same thing, but with nanoseconds. So it's going to be seconds and 10 to the 9th nanoseconds. Seconds cancel out. What are we left? We are left with this 5. We are left with this 10 to the 3rd and this 10 to the 9th. So let's just look at it like 10 to the 9th, 10 to the 3rd nanoseconds, or 5 times 10 to the 6th, or 5 million. Nanoseconds. And honestly, if you just want to go straight from milliseconds to nanoseconds, you can. It's pretty much 10 to the 3rd, 10 to the 9th, 5 milliseconds, milliseconds cancel, nanosecond, and we're left with 5 times 10 to the 6th. But that can get a little messy if you do like wrong conversion factor. So I usually just try to recommend how to do it how I did the first one. So we're gonna do milliseconds to microseconds. Same exact thing. Where's my pen? There it is. 7 milliseconds. We want to convert this back to seconds. So it's gonna be 10 times 10 to the 3rd. Oh, I'm so sorry. It's 10 to the 3rd milliseconds. 1 second. And we want to go into microseconds, which is 10 to the 6th. So we are looking at 7 times 10 to the 6th, 10 to the 3rd, or 7,000. Right, for the next conversions that we want to do, we want to both have one in base of 10 and base of 2. So for the first one, we want to divide by the power of 10, or figure out the power of 10. If you do remember that graph we had before, we had one column of powers of 10 showing you the units of powers of 10, and the second unit showing you the power of 2. Oh, and I'm so sorry, this one was not it. We're doing for these. So how many kilobytes in 5 gigabytes? So let's say power of 10 right here for this one. Alright, so let's start with gigabytes. It's going to be 5 gigabytes. So how many kilobytes are in 1 gigabyte? If you remember, in gigabytes it's to the power of 10 to the 9th, and kilobytes is power of 10 to the 3rd. And we can do just like we did before, a gigabyte, 1 gigabyte, and we want to do it to the lowest factor, which in this case it's bytes. So that's 10 to the 9th bytes. Just like I said, 2 gigabytes is 10 to the 9th, kilobytes is 10 to the 3rd. That looks like a 3. And now we want to go back to kilobytes. So like I said, let me clear this out. Like I said, it's 10 to the 3rd bytes in kilobytes. It's 1 kilobyte. Gigabytes cancel. Bytes cancel. We're left with kilobytes 5 times 10 to the 6th, or 5 million. Now we want to find to the power of 2. So if you remember in the graph, gigabytes is 2 to the 30, kilobytes is 2 to the 10, So what we want to find out is how many gigabytes it's going to be. So it's 5 times 2 to the 30 divided 2 to the 10. It's going to be 5 times 2 to the 20. And that answer, don't have it off the top of my head, it's going to be 5. It's going to be 5. There you go. So this is the first answer right here is to the power of 10. And the second answer right here is to the power of 2. Moving on. So for this one, we're trying to convert megabytes into kilobytes. Again, we're going to do power of 10 and we're going to do power of 2. So 6 megabytes. This one's going to be power of 10. So it's 10 to the 6 megabytes. Oops. Here we want to have the higher one. So it's 1 megabyte. 10 to the 6 bytes. We want to cancel out bytes. So how many in kilobytes? It's 10 to the 3rd bytes. 1 kilobyte. Megabytes cancel. Bytes cancel. We're left with kilobytes. We're left with 6 times 10 to the 6 over 10 to the 3rd, or 6,000 in powers of 10. 6,000 in power of 10. Now we're going to do in powers of 2. So what is megabytes in power of 2? It's 2 to the 20. What is kilobytes in power of 2? Same thing as last time. It is, sorry about that, it is 2 to the 10th. So what we have is 6 times 2 to the 20 and 2 to the 10. So that's going to leave us in powers of 2 with 16144. I believe it may be off by 1 or 2, but I believe that's correct. So it's 6,000 in powers of 10, and it's 6,144 in powers of 2. Moving on, now we're converting gigabytes into megabytes. Again, powers 10, 20 gigabytes, 1 gigabyte right here. Let's say gigabytes here as well. And there's 10 to the 9th bytes. This is a byte. And in megabytes, there are 10 to the 6 bytes. And 1 megabyte. Gigabytes cancel, bytes cancel. So that leaves us with 20 times 10 to the 9th and 10 to the 6th. So that looks like it'll be around 20,000. In powers of 2, we'll move on. Gigabytes is 2 to the 30. Megabytes is 2 to the 20. Now we have 20 times 2 to the 30. Divide 2 to the 20. So it's going to be 20 times 2 to the 10th. And that leaves us with 20,480. So as you can see, the powers of 2 are a little different than the powers of 10. For this one, it is fairly simple and easy. It's pretty much 50 megabytes 1 megabyte, 10 to the 6 bytes, and that's the answer. It's 50 times 10 to the 6 bytes. Powers of 2, if you can remember, megabytes is 2 to the 20. That's it. 50 times 2 to the 20. This is 50. And that's 52. 488. 8. 800. Kilobytes and gigabytes. 20 GBs. 10 to the 9th bytes. 10 to the 3rd bytes. 1 kilobyte. So it's going to be 20 mil. Powers of 2 is 20 times 2 to the 30 over 2 to the 10. And that's going to equal 20, 9, 7, 1, 520. Alright, so explain why modern computers consist of multiple abstract levels. So these modern computers consist of these different levels because it increases efficiency and makes user programmers' interactions with processes more level. It makes this easier to create. If you remember the divide and conquer rule, or implementation when creating these higher level computers, it allows us to separate these levels and allows us to these levels to perform specific tasks, and allow us to interact with all the levels. If you remember, level 6 is user level, and it goes all the way down to digital logic. So the 6th level is user, 5th level, high level, programming language, yada yada yada. So all these levels are created for specific tasks. For example, the user level is only for the user level. You don't see behind the scenes of the computer. You don't see machine language or assembly language. No, you only show what you want the user to see. And this occurs because each level only needs to perform its specific task and to interact with other levels. So say you have these 6, 7 levels that you have, but they don't perform or cooperate with each of itself, then you don't have a computer because these won't work. So you create these levels to have their own specific tasks, but allow them to interact with each other. So in the von Neumann model, what are the building components of the central processing unit? If you think of this picture right here, this is a CPU right here. What exactly do you see? You see an ALU, and we've seen this plenty of times. You see an ALU. You see this control unit, let's just say CU, and you see these registers or program counter. You can include both of them if you like. We can either say the PC, the program counter, or we can have the registers. So what do we have? We have the processing unit, which is the whole entire the CPU. The processing unit is this whole entire thing. It's the CPU. So this thing right here, this is the processing unit with included different implementations of hardware of the ALU and a control unit. So what we have in our registers is we have a program counter, and this is a register that contains the address of the next instruction that is to be executed. It always contains the next instruction to be executed. For example, when we finally move the instruction into the instruction register, which implements that instruction currently, the program counter will be moved up one so it can allow another instruction that will be for the next fetch decode execute cycle. So as each instruction is fetched, the program counter points to the next instruction that is to be executed. Then we have the ALU, like we said. This performs the arithmetic and logical operations that we need, such as NAND, or and NAND. So different XOR, different logical operations, which is very important. It can subtract, divide, multiply, and add. Then we have the control unit, which is probably the most important. I've bet you've heard me say this several times at least, but this is the central nervous system of the CPU, and this determines how instructions should be executed, including the operations that need to occur, as well as the operands it needs to fetch. Without the control unit, the fetch, decode, and execute cycle will not perform properly. So what is the von Neumann bottleneck? The von Neumann bottleneck is specifically talking about this memory pass from the CPU. It's from the CPU. Give me 1 second. So it's from the CPU to main memory. Can go either way. If you can see here, there's only one path. And think about high-level computers. If there's a problem, if there's like interrupt or there's too much information that needs to be fed during this path, it can cause congestion. Or like, think about a highway. Imagine if we changed a big highway into a one-way street. Think about how long the lines would be. It would just slow down the computer, the transfer of information in the computer. So, as a simple version, it's a single data path between the CPU and main memory. If you want a little bit of a more detailed version, it goes as it is a limitation caused by sharing the same bus for program memory and data memory. So the bus can only access either program memory or data memory, and the required time to process large amounts of data increases as a result. And you can go back into my highway analogy. Imagine turning a 3 or 4 lane highway into a one way, or just two way, so one street on each way. The congestion that you would see in that highway would be immense, and this can be an analogy to just the process of large amounts of data increases. The time increases. So just explain to me what it means to fetch. So what it means to fetch is to retrieve the next program instruction from memory. So what happens is that the program counter gets copied into MAR, then that instruction is read from the MBR. The MBR takes that instruction and copies it into the instruction register, and the program counter is incremented. And of course, the program counter always points to the next program instruction. So, tell me what happens. PC, what MAR does is that it copies, or we can even switch. This is what happens. PC. I'm going to flip the arrows because it's actually convention to do it as this as well. Because remember, PC is not copying its instructions into MAR. MAR is the one that's going into PC. So what's happening is the memory address register is copying the location in memory where PC has the instruction at. So what's in MAR, it's just a location in memory. And what MBR does, it goes and finds the instructions in memory. It's no longer pointing to memory. That's what MAR does. MAR points to memory. So if you can think about it as a very simplified version, let's say this over here is just a point in memory. And let's say 001 is the address. So MAR is pointing to the instruction, and what MBR does, it reads MAR, it can locate what point in memory MAR has, and it goes to that memory. It's a very, very simplified version. And it copies whatever instruction or data or anything like that is in this memory, and now MBR actually has the instructions for whatever the instructions in address 001, it has it in MBR now. Like I said, MAR has it's pointing to memory. It doesn't have the instructions. It's just pointing to this location right here. But what MBR does, it copies whatever inside. Pointer options. So MAR. Then we have the memory buffer register, or it can be MDR, which is the memory data register, but I don't use MDR. So what happens next? MBR now copies its information into the instruction register. And what does the instruction register do? The instruction register holds the instructions that is currently being executed. So at this point, whatever instructions in here is currently being executed. And what happens now? PC is now adding 1. So PC is incremented by 1, and it holds the next instruction that is to be executed. So it's a very simplified version, but I hope you guys are understanding what's happening. So instructions to retrieve the next program instruction from memory. So the program counter gets copied into memory address. So PC is copied by MAR. Then the next thing is the MBR reads from MAR, the address of MAR. Or it holds the address. It points to a location in memory MAR does. Then the MBR is copied into the instruction register, and then PC is incremented by 1. So how does the fetch, decode, execution cycle work? So there's fetch, decode, and execute in all parts of these. So in the fetch part, the control unit fetches the next program instruction from memory using the program counter I hope you guys are used to the program counter because I've already been talking it a good amount of time. So it's the code part. The instruction is decoded into a language that ALU can understand so it can perform any operation that it needs to. And there are some operands that need to be fetched as well to execute the instructions that are fetched from memory. And the execute portion of this cycle, the ALU executes the instruction and places the results in the registers or memory. So guys, that is the end of homework 1. I hope you guys had a good understanding or feel for the homework 1. Chapter 2 will be much harder, so become ready for chapter 2. And this is when we start playing around with binary, hexadecimal, and octo numbers. So I hope you guys enjoyed this video. There was a lot of information during this video that could be helpful in future videos. I inserted more knowledge than the class actually requires you to do, but it helps you start building that foundation of a good base of computer organization. And I think it's very, very important to learn that information. Well, thank you guys. Leave a like, comment, subscribe. This is Everything Program. I hope you guys have a nice day.